effectively is that everything on that side of the strain ellipse, or the undeformed or the circle, I guess you call it, everything that starts out on this side of the circle to become the strain ellipse will first shorten and then stretch. So a whole range of markers start in that direction and switch. The ones on the other side always stretch. And that's completely different than this one, right? In this configuration, this line element always shortens. These line elements always stretch. There's fields in here that are always stretched, these are always shortened. But some of these line elements actually also do the same thing, in the sense that as they rotate, take that one for example, it initially shortens, but eventually it also stretches. So this occurs in both pure shear and simple shear. It's just much more prominent in simple shear because there's a much larger field that experiences that effect. But it's an important thing to remember is then that local deformation can get confused by the flow in this particular sense. Now I should have shown these before to talk about these. You take your time and look at some of these. It's actually really useful to look at some of these animations. There's several other of these around. I just like this guy's site. And we'll see whether this takes forever. I should have started this before. Go away, Windows. Oh, here we go. Okay, so here's just some, I like this thing because it's got some nice features. Here's just an example of this. Watch this little movie. This is just pure shear. And it shows kind of a couple of things that are not so obvious in this context. Watch what the particle paths do. They're very strange also in that the particle flows at the local scales relative to this scale flow towards the stretching direction, and they are symmetric about this direction. It's that flow path that gives rise to that coaxiality of the strain. So what's weird and counterintuitive here is the simplest one, the simplest case in terms of coaxial strain and stresses has the most complicated local flow pattern because it has to flow that way to maintain that relationship. If you compare that to, end these, go back, I just go back, right? Compare that to, I think that's the right one, simple shear. The flow paths are simple, right? They're just going like that. But the strain, the strain accumulation is more complex. Now, one thing I should emphasize is the real world is hardly ever either one of these end members, which is the bad news. It's usually kind of towards one or towards the other, but there's usually some kind of a hybrid betwixt the two in the real world. Yes, sir?
Well, I was going to ask something related to that. As far as like perspective, when you're looking at something in an outcrop, like how do you know it's just not your perspective?
I'm getting to that. This is simply a two-dimensional view. You're very correct. This is a two-dimensional slice of the system, and you have to know the right slice to look at in this context. What we're doing now is sort of just a theoretical treatment. I'll come back and give you some geologic examples in just a moment. But take some time and go to this website. These are on the, oops, that's wrong. There's one other one I'm going to show you. Here's one that shows some of these effects, I think. Here's this one that shows some of this effect I was talking about. How you could have markers that start at some orientation, and they shorten and then stretch, or something of that particular sort. Both of those are important relationship. This one here is, say, boudinage, and this one gets folded, see? And like I said, take your time and look at these. He's got some pretty good description. Oh, yeah, here, this is what's fun. If you're a paleontologist, there's what your fossils look like after they become good rocks, right? Anyway, that you can follow those and spend some time on that. But it's a really good way to help visualize what's going on in this context. Okay, so let's talk about some simple applications of this. And the first application that this was actually applied to is one of the sort of the first sort of theoretical applications of strain theory to the geologic problem was in the analysis of what are called shear zones. A shear zone is just what I was talking about, the flow equivalent of a fault. So material is bounded by a band of undeformed rock, and the rock in between shears, so it's like a fault with distributed motion within the fault. And here's a book, this is from a textbook showing rocks. This is essentially a gabbro that surrounds it, and in the middle are the same minerals come in here and are get stretched out, right? Here, the minerals are acting, the minerals, in this particular case, take a blob of this material, imagine it as a very irregular stringolith, right? So as it gets caught up in the flow, in these positions, it gets stretched and shortened. So these objects within the shear zone are streaked out. They're recording, or they're basically tracking the finite strain in the context of that model. What do you think that angle would be, right? Here's the edges of the shear zone, and there's the long axes of those objects. What do you think that angle is? No, I mean, what do you think that angle represents? Relative to this theory. The objects get streaked out. What do they represent in this context? What did I say was the characteristic about the finite stringolithsoid and the shear zone itself?
That you get the particles elongated. So
Yes, but more specifically, what about this shape?
if they're symmetrical about each other.
Here's another one. What did I point out to on this graph? Remember that?
That as the angle increases, you get
This angle.
the ellipsoid is becoming bigger.
Yeah, but it's also, this angle changes as a function of the amount of accumulated strain. Or an alternatively, a better way, maybe a simpler way to think of it, is this is the margins of the zone of shear. This angle would be, well, this would be the shape of objects that get trapped in the flow. So let's go to the coordinate system.
Oh. That's about the same.
Maybe this is easier to see. Here are objects. There's one that's undeformed. As you move into the zone, those objects get squished and pulled, or stretched in one direction and shortened in another direction. You can see them here. These objects as you approach the center of the zone. That is finite strain, accumulation in the zone of shear. Here, the objects I started with, you have some sort of crystal shapes. They get strung out. Their long axis relative to this system, that's the angle theta, or theta prime that was shown on that graph. One of the things that's pretty cool about that is that all you have to do is take a protractor and measure that angle, and you know the amount of finite strain, you know the amount of shear that occurred within that zone by that theory. You know the displacement. And you could also predict what the finite strain was, and you could compare that directly to object shapes, or go back and forth between the two. In fact, that's done routinely. So here you could do the same thing by looking at the object shape as a measure of finite strain. You could take the object shape and calculate what theta prime would be, or what, so you would know what the angle were, and you could check back and forth between the shape and the angle to estimate the amount of displacement across the zone. Or another way of looking at it, these trajectories of the shapes of objects are related to the accumulation of strain. So where, for example, where is the greatest strain in this trajectory? If these trajectories show the finite strain trajectories related to that angle theta prime, where theta prime gets smaller and smaller as it accumulates, where is the maximum strain in the zone? in the middle, because that's where the maximum amount of rotation is. In fact, it's very sharp in the middle, because these are virtually parallel, such that the angle between the edges of the zone and this is maybe 5-10 degrees. So most of the strain is in the middle of this particular feature, and that's fairly common. There's a second very important relationship, though, that if you got nothing else out of this relationship, note an asymmetry relationship here. There's a zone, or that zone, in which these trajectories are inclined to the edges of the shear zone, of the zone of shear. Now, so relative to that model, excuse me, let me draw a picture here if you can see this. Think about this problem. I can shear this in one sense, or I can shear it the other way. Can you see that in the back of the room? Let me just turn the light on so you can see it better for the guys that are in the back. Light. So if you start with, that's useless. Here's a strain ellipse. Axis of the strain ellipse is the long axis of objects. And there's this angle theta prime. Here's this long axis, theta prime. What's a real simple generalization in this, in terms of the trajectory of those object shapes, in terms of which way did it go? In this case, which way did it go? Did it go top right, or did it go top left?
Wouldn't it be also your perspective cutting it? So if you're standing on the
Oh,
other
sure.
side looking at it that way.
But I'm not, you're looking this way. That's correct, that is correct, just like anything. But actually, well, yeah, that's right, it wouldn't in that sense. But all I want to know is the sense of shear, right? Powerful thing to know. So so you said it back there, but anybody else?
Top right.
Top right. It has to match this, right?
Mhm.
Because it's asymmetric in this sense. Otherwise, it would go the other way. Asymmetry would go this way,
Mhm.
right? That's a very, very powerful tool. Just knowing whether something, that's like knowing the difference between a normal fault and a thrust fault, right? Kind of a big deal to know the distinction. And so shear sense is a very important thing to recognize in rocks that have ductile flow or strain features that are